Before we start checking what you guys put, though, we're going to do it really fast, and we need to transition to 4.2. I know. But here's something that I see CalcAB kids and BC kids make mistakes on, and it messes them up in the free response. You guys know what I'm talking about? Long answer. The free response justifications. Free response justifications. Because in free response questions, very commonly, especially when it has something to do with finding relative extrema or absolute extrema, or explaining what it is that you're solving for to show that you kind of understand the story of the word problem, they're going to say explain or justify. And what I'm about to ask you has messed up time and time again calculus students in their justifications, okay? What I'm asking you is, are decreasing and negative synonymous? Pause. What do I mean by synonymous? Synonyms. It's a grammar term for words that are alike, and not just are alike, but can be interchanged, right? Have similar enough meanings, they can be interchanged. Are decreasing and negative synonymous? Yes or no? Absolutely not. Why? Negative refers to the sign of a quantity, positive or negative. That's all it refers to. If you want to think about it, in your original graphs, you could think of, or even in your derivative graphs, above or below. That's all it means. The values are negative or the values are positive. Now, that can relate if velocity is negative or velocity is positive. That can tell us something like the object is moving to the right or moving to the left. Negative and positive can mean something, and it definitely does. But as far as like a graph or a quantity is concerned, negative is below, positive is above. It talks about the numeric quantity, the sign, S-I-G-N. What does decreasing refer to? The slope. Kind of. Indicated by the slope. Decreasing is indicated by the slope because decreasing, a quantity will be decreasing when its slope, the quantity slope. Let's say f is decreasing when f's slope is negative. Good. I mean, you could say down, but negative sounds a lot better. F is decreasing when f's slope is negative. But doesn't it also refer to emotion? Doesn't it also refer to a behavior of the quantity or of whatever it is that you're talking about that's decreasing? So on this sheet, if I say the blank should be negative and you put decreasing, are you right or wrong? Wrong, because you're talking about how it's behaving. I'm just talking about the sign of the quantity. Do you understand kind of the difference? So what also is not synonymous? Increasing and positive. Good. Positive and increasing, they're not synonymous. So let's talk through this, but I needed you guys to get that. Decreasing and negative, even though negative of a quantity refers to decreasing of a different quantity, negative of a slope refers to decreasing of the original. Even though they are related, they are not synonymous. Okay, if velocity is negative and acceleration is positive, are opposite, then speed is decreasing. If you put that, you are totally correct. What's another way of saying speed is decreasing? The object is slowing down, right? If velocity is positive and speed is decreasing, then why am I going to fill in the blank with acceleration is negative? Good. If speed is decreasing, the signs have to be opposite. Good. If velocity is positive and decreasing, then speed is decreasing. Specifically, why? If velocity is positive and decreasing, speed is not decreasing because velocity is decreasing, but because velocity is positive and acceleration is negative. Good. If speed is increasing and acceleration is negative, then velocity is negative because the signs need to be the same if speed is increasing. If something's speeding up and acceleration is pushing it left, it must have already been going left to begin with. Is this kind of making sense? Good. Number 5, if velocity is negative and increasing, then speed is, I knew I'd get some of you on that one. Why is the answer decreasing? Absolutely, positively, absolutely no other way about it. Pause. Why did some of your classmates say increasing? Velocity increasing, speed increasing. Oh, it's obvious. Got it. Mm-mm. Velocity is negative, which means my object is moving left to your left, right? Yeah. Okay. But what's acceleration doing? Pushing the other direction. It's trying to increase the numeric values. So that's the example of like -1, -4, -8. No. Increasing. Speed is decreasing. Negative. -16, -8, -4, -2, -1. It was like that case that you guys did in your motion packet. But long story short, as long as you break it down, you'll be fine, because the signs of velocity and acceleration either need to be the same or opposite. What's acceleration if velocity is increasing? So what's true if I have a negative velocity and a positive acceleration? The only answer is decreasing. Make a note. If you got that one wrong, make a note. Show yourself. This is where us and cars get confusing. Velocity increasing. I got it. Speeding up. Nope, 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 nope. They're working against each other, slowing down. If the particle is moving to the left, ooh, translate that for me. Moving to the left, what do I know? Velocity is negative. And speed is decreasing. What do I know? Signs are different of acceleration, so I have opposite signs, opposite velocity and acceleration. Then acceleration is, well, opposite. If velocity is negative, what's acceleration have to be? Take a second. Make any notes that you need about anything that you missed. Do you guys have any questions you want to ask me? Because this does get tricky.
So if the signs of velocity and acceleration are opposite, then speed is
Automatically. Good. However it shows up. So when you see words like velocity increasing, velocity decreasing, etc., you have to translate that to what does that mean about acceleration, positive or negative? And then you can compare those two signs. Yeah. I like number 6 because it makes it really obvious. Speed is decreasing tells us opposite signs. Then go looking for, what do I know? Oh, velocity is negative. Okay, acceleration positive. That shows a big understanding. That one, if you're able to get number 6, and then number 5 was really tricky also. Because the velocity was increasing, but since it was negative, that means the speed was decreasing. They're working against each other, the object's slowing down. All right, cool kids, go ahead and put this blue sheet away in a safe place. Just because it is a great one for speeding up, slowing down. But in your notes, didn't we get this one written down on Friday? Maybe, because you're going to be making this a forever card. But a forever card is only as useful as its practical application. I know that's really hard in things like MVT and IVT, but you've seen multiple times where with MVT and IVT, not multiple times, but at least here and there, where that could come up in a free response question. Speed increasing, speed decreasing. It could show up in a free response. It could show up in a multiple choice. Where is something speeding up? Where is something slowing down? Make yourself any notes that you want before we move on from this topic. You just took a little baby quiz over the weekend. You talked about it in your group. Some of you changed answers before we ever graded. Yourself a little note about the opposite signs, the same signs. Maybe make yourself a little note about, hey, if I see velocity increasing, decreasing, brain, think about acceleration's signs, positive or negative. Whatever you need, make a little note to yourself, just so that whenever you are looking in your notes at this topic, you'll be reminded. The other thing I would do, not that I'm going to make you do it in the forever card, but as far as a how-to, as far as how to practically use this, you need to compare. It's up to you whether or not you put it in your forever card. I won't ask for it on a forever quiz. But the how-to of speed increasing and decreasing is compare the sign charts of velocity and acceleration marked by both. How do we usually do sign charts, guys? How do we actually like put numbers in the sign charts? Where do those come from? Critical numbers. So either the critical numbers of, maybe put it a little bit better, we'll do by both the velocity of t equals 0 or d and e, which we would call resting points, numbers of position. And if we're doing velocity and acceleration, here's where some people get stuck. You have to look at the zeros and d and e's of both velocity and acceleration, because we're looking at both of them. In a sense, if you want to think about it, we're making one big old sign chart, thinking about speed increasing, decreasing as our final conclusion, and we're thinking about the signs of both acceleration and velocity. So in this one, it's like a double-decker. You guys have seen those double-decker buses in England, right? There are even double-decker planes. Those are kind of scary. I've only been on one like once. Double-decker trains. There are all kinds of double-deckers. It's a double-decker sign chart. You have to think about both acceleration and velocity. And so we're going to put in the zeros and the d and e's of both velocity and acceleration. And then just look at the two and say, okay, are they both positive? Is one positive? Is one negative? As we look at the intervals formed by the zeros and d and e's of both, we're going to ask ourselves, same or opposite, and then we'll know speeding up or slowing down. That's a quick little problem solving hint, how to apply the forever card to a motion problem, okay? With that, section 4.2. What on earth is going on with area? Now, these are the notes that you guys are supposed to have ready for me from the weekend. If you don't have it ready for me, long story short, you're just not going to have time to write it all down. But I am going to fill in a few things, and if you need to, you can just say, oh, I don't have them written down, so I'm pretty sure that the properties, she's not going to give me time to write down, so I'll skip 3 lines, and I'll go to the PDF tonight, or I'll go to the YouTube video tonight. Speaking of going to the PDF, speaking of going to the YouTube video, oh, I closed it? Sad day. If this homework is due tomorrow, where are you going to be submitting it? Google Classroom. Google Classroom, what did I put in there underneath the actual classwork? Where are all your nifty links to everything for this class, including the calendar, including the YouTube channel, including the shared folder, which has your notes, your PDF copies every day. Remember, it's right underneath the classwork at the very top. If you need to get to the YouTube channel or to our class calendar, see when our next test is. Ooh, maybe we should peek at that. But what else is in here? Didn't I put down the sweatshirt design, and didn't I put down prices real quick? So there's a short sleeve t-shirt. We're going to be hitting the 25. I doubt we're hitting the 50. So plan on that plus tax. I'll get you a final amount once they get me the invoice. Sweatshirts, that's a crew neck. Pullover, that's a normal hoodie. Zip is going to have a hoodie also. And then I also threw in, Grace, you asked about the long sleeve t-shirts. There they are. So I'm going to go ahead, and as we're taking notes today, I'm going to pass this around. I'm going to do it today and tomorrow. Hopefully, maybe someone can text Thomas or I can text him. But we want to get the order in ASAP because some of you guys are like, it's cold outside. I know, me too. So anyway, just put your name next to a number and then what you want as far as short sleeve, long sleeve. That's going to be t-shirt. I actually write it here. Short tee, long tee, crew, hoodie, or zip. And the zip has a hoodie also. And then give me your size and just, it's based on, I mean, you guys have gotten a lot of things from Impact. That's who does sports. That's who does almost all the classes. So go ahead and pass around. I'll pass around again tomorrow. You guys have seen the prices. If you need to talk to parents, et cetera, please do so. But otherwise, there we go. Mr. Richmond said either logo is okay. So do we have a strong opinion between the academic and the other one? The other one being a warrior. The one with whoosh, and then his little plume is like whoosh, looks like hair, but it's not. You don't have a strong opinion? Okay, we'll let period 6 determine. They have strong opinions all the time. They always have strong opinions. Where's our next test? Next Friday. The forever quiz is the day before. The test review is the day before. P.S. Our test has 2 parts, just to be aware. So even though our test is Friday, it's also Thursday. There's a forever quiz and then part 1 of the test, all in one day. So kind of just be planning ahead as we're thinking through practicing, et cetera, et cetera. All right, summations. Has anybody ever practiced for your SAT and done a sigma or a sum? Or do you remember it from last year? How do we do these guys? Start at 0, say he's a variable, and we plug him in. These are sums. They're called summations. They have a sigma, Greek letter, as a notation, but really it just means plug in the 0, plug in the 1, plug in the 2. It's repeated addition all the way up to 9 squared. There's a lower bound, there's an upper bound, a beginning and an ending. Sigma, summation notation, is a way of giving a formula and saying, hey, repeat this addition over and over and over, please. And that's going to be important for what we're about to do. What's the difference between number 1 and number 2? Good. The first one stops, it's finite, and the second one just keeps going to infinity. Now, there are some properties of summations, like you can pull out a constant. Because if you think about it, if there was something like 5k squared, it'd be 5 times 5, 5 times 5 times. And what can we do whenever it's a GCF? We can pull it out. So pulling out that constant, we can split up addition. Because if you were to think about it, if it was k squared plus 1, it could be 0 squared plus 1 squared plus 1 plus 3 squared plus 1. We could separate them and have all the squareds plus all the 1s. Or any other 2 different sums that we have. And the same thing works for differences. Sums or differences. I'm about to change the page, skip however many lines you need in 3 and 2 and 1. Why on earth was I showing you sigma notation and reminding you of that whole idea of how we can give an equation and we can actually have a sum be condensed, even a big sum that follows a certain pattern be condensed? Because we need those things to define an integral. We talked about at the very, 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 very beginning of the year how there are 2 big problems to calculus, at least calculus 1. One of them is the slope of the tangent line. Remember that guy? We did secant lines, and we got closer, 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 closer to the tangent. Ultimately ended up being a limit of the slope of secant lines, the difference quotient, defining f prime, and then we had all these shortcut rules, which some of them were still long because some things were still quite complicated. But the first big question was the slope of the tangent line. That's answered by a derivative. The second big question is how to find the area between a function's graph and the horizontal axis, aka most people would say the area under a curve. Not the area under a line, that's easy. It's a trapezoid, it's a triangle. Not the area under a circle, that's easy, it's geometric. Not the area under a straight line, that's a rectangle or a square. But under a curve. Whenever a boundary is defined by a curve that's non-geometric, there's no way to do it without calculus. However, the cool thing is that integration, what we've been doing with antiderivatives, somehow ties together with this area problem. That was the second big question that calculus answered. Now, I just said, calculus, though, is only necessary when the shape formed is non-geometric. So if we were to take this first shape, for instance, negative 2x plus 3, well, that's not a shape, it's just a line, right? Hopefully, we remember y equals mx plus b, right? We always graph the y-intercept first, the b, and then we go and graph the slope to get our points. So I would start off by going, let me get at least a few little tick marks here. The y-intercept is going to be positive 3. We're going to go down 2 over 1, down 2 over 1. We could keep on going. Long story short, we have a straight line. However, what's going to be a little bit different from what we've done before, even in pre-cal or even in Algebra 2 or Algebra 1, is that they're not just going to ask us for the entire function. They're going to give us, with this area problem, some sort of beginning. We're not dealing with infinite areas or infinite intervals. That's CalcBC. They're called improper integrals. We're dealing with an actual figure, an actual shape that has a beginning and an end. So starting at x equals 0, if we were to actually draw like a boundary using that vertical line, x equals 0, and then x equals 3 halves. Did you guys realize x equals 3 halves is the same thing as the x-intercept? If we were to cut off this line between those 2 portions, technically, we'd only have this portion of the line. And then what did I just define on the page before? Area under a function between it and the horizontal axis. So what area am I actually talking about? Guys, what shape is that? Yeah, you don't need calculus. All you do is, easy, 1/2. What's your base? Well, I was thinking base as being the horizontal, then we'll do height as the 3. So we could put the height, someone said 3. You're right, that's one of them. But then the base is going to hit at, sorry, I didn't actually label, but yeah, 3/2. Or 1.5. You could plug in x is 0 to get your intercept. It's going to be positive 3/2. But here's the crazy thing. When we solve this and when we end up with 9/4, if you guys had your calculator near, which I'm not going to make you do today, but if you had your calculator near, I would have you go to the math menu, go to something that we did at the very beginning of the year, and find your integral that had bounds. It would be underneath the math menu. I think it's FNINT, function integrate. It's also under the shortcut menu. And I would have you put in 0 and 3/2 as your lower and upper bounds. I would have you put in your negative 2x plus 3 as your integrand, and a dx. What's different from this integral from the ones that we were doing all in section 4.1? They're bounds. Why are you yellow? This is what we call a definite integral. So this means I could have basically taught you the beginning of integration back in Algebra 1. Awkward. Yeah. But she wouldn't have been able to go any farther than these shapes. Now hold on, wait a minute. Are there any other shapes that would ever form underneath a line that we could do? Because this one just happens to hit at the x-axis. How do you guys think we would do something if we had maybe something like the integral from, let's do 0 to 3 of x. Okay. How is this one going to be different? My intercept is going to be now at 5. I'm going to go down 1, over 1, down 1, over 1, down 1, over 1. Wait a minute. Hold on. X is 0, x is 1, x is 2, x is 3. Stink. That's all I've got. But if we were to cut it from x equals 0, even though the line goes on forever, is this still geometric? Yeah. But what would you have to do this time to find the area? Instead of a triangle, instead you'd just be like, oh, whatever, I know geometry. As long as the boundaries are linear, I can do it. How would you guys find this area? Yeah, that's what I'd probably do too, right? The square, or probably the rectangle. Do the rectangle plus the triangle, but isn't there also a geometric figure that looks like this? What's that? Trapezoid. But you guys could be creative. We could do the rectangle, we could do the triangle, or we could do a trapezoid. Either way, we'd be fine. So would a line always form some sort of geometric figure? Yeah. What if it's a straight line? It's going to be a rectangle or a square if it's the same dimensions, length and width, right? If it's this way, it could be a trapezoid, it could be a triangle. What if it goes below the function, below the x-axis, below the x equals 0 line, y equals 0 line? We'll talk about that. But we already kind of did about how there's positive change and there's negative change, moving right and moving left with derivatives. Anyway, we'll get there. But the deal is with linear functions, we're okay. But as soon as I give you the next most basic function, constant functions, okay, straight lines, rectangles or squares. Linear functions, that was the next thing you learned probably in Algebra 1. Then you learn quadratics. They're the next most basic function, elementary function, no big deal. Why is it now impossible? Because what's the boundary, guys? If I was to do the exact same thing I just did, Draw a function, super easy. It's a parabola, shift step 2. We can draw that, hopefully somewhat in our sleep if we needed to. I'm going to cut this down just to be between 0 and 1. Why is he so much harder? Linear, I don't mind. Linear, I don't mind. Linear, I don't mind. What's that? Oh, I mind. Now, could we do a trapezoid? Yeah. Would we be close? Yeah. But in math, is close usually a good thing? So what do we do? You guys could go to your calculator and you could plug it in. You could see exactly what it was by going from 0 to 1 of x squared plus 2 dx. However, let me just show you a peek at where we're going, not in this section, but in future sections. This section is all about area, and if we can't find it exactly, we're going to approximate, because maybe you remember, I told you not all integrals can be integrated by hand. We're looking at the most basic ones. We're looking at the most basic ones that can be integrated by hand, but not all can be integrated by hand. So there has to be these approximation techniques that we're going to learn in this section to deal with those harder ones that we couldn't possibly do by hand. But let me show you, since this one's a basic one, we could totally anti-derive him. Let me show you where we're going to eventually get. You guys good so far? Well, where's the plus c? Well, I guess we could put him if we want. You could put the plus c. You could put the plus c, but the plus c minus a plus c will always cancel. It doesn't really matter. What do you guys see that I just did? Oh, I put squared instead of cubed. Besides the fact I can't rewrite. What did you see that I just did? Plugged in the 1, and then I plugged in the 0, and what's in between? But why? There's something called the fundamental theorem of calculus. I'm just giving you a quick little preview of where we're going. How do we solve one of these guys? We have to anti-derive first. We actually ignore the plus c just to save ourselves time. We plug in the top bound, we plug in the bottom bound, one big subtraction, and we can find what ultimately used to be impossible. This is going to end up being 7/3 if you plug it in your calculator. But how? Well, to get to fundamental theorem of calculus, we have to kind of do what we did with the derivative. I could have showed you the shortcut rules way at the beginning of derivatives and been like, just do this. But the problem is for the AP and for your understanding, we had to start with the limit definition. So even though this is how we're going to eventually solve integrals, whichever ones are possible to solve by hand, we have to go back to the beginning and say, hold on, we have an impossible area. What approximation techniques are there? And how on earth can that possibly lead us to that one little simple subtraction of two antiderivatives with the bounds plugged in? How is that possible? So I kind of showed you a peek behind the curtain if you're a Wizard of Oz fan. I kind of showed you a little bit of the behind the scenes of what we're actually going to be doing, where we're actually going to be heading. But because of the AP partially, because of your understanding of an integral as well, I have to show you the approximation and how on earth that leads up to an integral. So the rectangle method. If you guys just noticed what I just showed you, the area under the parabola, I was like, hey, it's kind of like a trapezoid. But not every figure is kind of like a trapezoid. What would you guys say this figure kind of is? I don't know, a rectangle minus a semicircle maybe? Or a trapezoid, take away a lot of stuff, or a rectangle and a little semicircle and a triangle. Depending on what the figure looks like, you could use all sorts of different shapes to try to approximate it. So instead of going through all of that and realizing there is still this idea of infinitesimal, how we can get closer and closer and closer and closer, instead we're only going to focus on rectangles. We'll do trapezoids a little bit too, but not until later. And here's how the rectangle method works. Notes that you should have already written. You're going to take an interval, a beginning and an end, an A and a B. And what we already talked about was those are the same things, just kind of showing you a peek at where we're headed as the bounds of a definite integral. The A and the B, the beginning and the end. We're going to take that overall distance, we're going to split it. If we're able to do it by hand, we're going to split it into n equally spaced sections just to make things simple. So the way we do that is actually quite easy. We can say delta x, or the change in x, is going to be b minus a, take that distance, and then cut it in n pieces. No big deal. Maybe we can approximate with 2 rectangles, or 5 rectangles, or 10 rectangles, or 100 rectangles, or 1,000 rectangles. Oh my goodness. Sounds like a limit's coming. We're going to find the area of the rectangles, a equals b times h, because what we're going to do is once we decide to split this into 3, for instance, or once we decide to split this into 6, for instance, or once we decide to split this into maybe 12, for instance, then we're going to go ahead and with each of these little subsections, we're going to make rectangles. And one rectangle would have not been a very good approximation, but once you start putting in more and more and more rectangles, okay, obviously my spacing was off. But once you start putting in more and more and more rectangles, well, the error is going to get lower and lower and lower. And if we can somehow get a limit in here, maybe we can get there, just like we did with slopes of tangents. But if you look at this, my rectangle is never going to go beyond, well, maybe on one side it will, because there's not a straight, constant portion of the graph. But even though one side goes beyond, I need to somehow hit or stop at the function. So my heights of my rectangles are going to somehow be determined by each of the different function values all along the way. So I'm not just going to say this height, I'm not just going to say this height, f of a or f of b. I'm going to actually just say f of x and say, you know what, somehow it's going to be determined by f of, we could call it x star. Some people would say f of x sub a. Some people would say something like f of c's, like c1, c2, c3. People sometimes put it many different ways because usually x equals a and x equals b is the beginning and the end, and some people like to just use a different letter like c, kind of like MVT, c's are in between. C1, c2, c3 as to where we go hit the curve, because it's going to change for every single subinterval. But the heights are somehow determined by hitting up at the curve, and the bases are always going to be determined by, well, basically delta x. If we equally space it, well, no big deal. They're all going to be the exact same base, and it's going to be nice. And why on earth are we trying to make it formulaic? Well, remember at the very beginning of today, didn't I say there's this really cool math thing called a sigma that says, hey, if you can give me some sort of formula to plug into, I can do for like the 0 subinterval and the first subinterval, second subinterval, third subinterval, I can plug in numbers and be like, hey, there you go, without me having to do all this work. Since we have this operation, since we have this ability to do repeated sums over and over and over again, and if I just said something like, hey, let's fit in 10 or 100 or 1,000, well, if we can somehow get a formula for all the different areas at all the different points, maybe this can all come together. So number 3 says find the summation of the areas of the rectangles. You will have the approximate area under the curve. Long story short, now approximate, because if I end this anywhere, approximate, but if I could say A is approximately, if I could throw a sigma in there, and if I could do some sort of K equals 0, or you could even start at 1, kind of depends on who you are as to where you start. Let's go ahead and start at 1. I think that's a kind of more common. So we could do the first, second, third, fourth, all the way up. Let's say we're doing n equals 10 subintervals. I could kind of say, okay, for whatever function, for whatever my f of x is, if I split my b minus a over n to be my delta x, b minus a would be actual constants, so I could do b minus a all over n would be 10. Those could be all of my bases. And you might be like, well, isn't it usually base times height? Why are you putting the bases at the end? Because these are my little delta x's. Well, usually, whenever we have a mathematical expression, especially with integrals, we put f of x first. So I'm kind of trying to move what we know, the number, the constant, over to the side. Then over here, we're going to actually deal with our f of x, whoever he is. Now, somehow, I need my f of to go through the interval and keep on, every time you plug in k, another interval over, go over, and go over, and go over, to go hit, and go hit, and go hit. So then I'm going to somehow have to put in something like b minus a all over n. I need to count by these. I could do something like that, to where it's f of the first b minus a over n. And then I could do f of the second b minus a over n. So I'm jumping, 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 plugging into my function. And here's how I have my, basically, bases times my heights. Is today chapel day, not tomorrow? Today's chapel day? That's what happens when you don't have a teacher's meeting when you come back. Hold on, I have Where Weekly up right here. Oh, that's a bummer. I thought chapel was tomorrow. All right, cool, kids. Dilio, homework's going to need to be due on Thursday. Okay? But I might post a video either today or tomorrow in Google Classroom. If I do, we better watch it. Okay? Sound good? All right. Bye, cool kids. See you later.